Let me start today with a weird challenge. Imagine you are holding the sharpest knife ever made, and I ask you to cut a distance in half. You cut it once, then you cut the half in half. Now, here is the question. Can you keep cutting forever? Most of us assume yes, space is continuous. You can always split it into smaller pieces, but modern physics has been whispering something else for decades. Maybe space and time are not infinitely divisible. Maybe reality has a smallest grain, and maybe that grain is not matter but information. And if that's true, then we have to accept a mind blowing and mind bending philosophy. Space time might be made of quantum bits, not as a metaphor, as a literal description of the universe's deepest layer. To see why serious scientists even entertain this, we have to watch physics get cornered step by step until it had no choice but to consider bits underneath space. In Newton's world, space and time were like a perfect theatre stage. The stage exists whether actors show up or not. Time flows whether anything happens or not. That was not naive, it was practical. Newton needed a stable reference to define motion, and it worked brilliantly for centuries. If physics were a story, Newton's universe is the calm beginning, a clean set of rules that feel complete. But then a tiny crack appeared. It was not a crack in motion, it was crack in time, and that crack had a name: light. Einstein started with a simple annoying observation. The speed of light seems to be the same for everyone, even if you are moving. That creates a problem because if speed is distance over time and everyone agrees on speed, then different observer must disagree about distance and time. So Einstein did the unthinkable. He merged them. Space and time became a single object, space-time. Then he went further. In general relativity, gravity is not a force pulling you. Gravity is the shape of space and time. Mass and energy tells space-time how to curve. Curve space-time tells matter how to move. Here is the key moment. Listen carefully. Einstein did not just change our map of the universe. He made the map itself alive. Space-time becomes something dynamic, flexible, physical. And once something becomes physical, physicists ask that dangerous question. If it can bend and change, what is it made of? Einstein did not answer that because at the same time another revolution was happening, one that hates smoothness: quantum mechanics. Quantum mechanics was born from confusion. Scientists tried to explain why hot objects glow the way they do, why atoms emit light in specific colors, why electrons don't simply crash into the nucleus. And the answer was shocking. Energy does not come in a smooth stream. It comes in chunks, not because we are bad at measuring, because that's how reality behaves. Then come the uncertainty principle, another brick in the wall. You can't perfectly pin down a particle's position and momentum at the same time. So the quantum world is not a smooth clockwork machine. It's jumpy, it's grainy, it's probabilistic. And now we reach the collision point. If space-time is physical and quantum rules apply to physical things, then space-time should have quantum behavior too, which means space-time itself should fluctuate, shake, fuzz, form. And when physicists tried to do the math, quantize gravity, the equations did not just get hard, they broke, they blew up into infinites. That was not just a technical headache, it was nature slamming a door. And the sign on the door said, smooth space-time is not the final story. So physicists went hunting for the boundary where smoothness dies. When you combine gravity, quantum mechanics and relativity, you get a natural scale called the Planck scale. Here's the simplest way to understand why it matters. To see very tiny things, you need very high energy. To see and high energy, light has shorter wavelength, so it can resolve smaller distances. But in Einstein's universe, energy is not passive. Energy curves space-time. So if you try to cram enough energy into a tiny region, you don't just measure the region, you collapse it into a black hole. That means the universe enforces a limit. Below a certain scale, the very act of measuring distance destroy the concept of distance. So the Planck length is not just small, it's a hint that space might not be infinitely divisible. Like pixels in an image, from far away everything looks smooth. Zoom is enough and you hit the grid. But what could the pixel of space be? At first some scientists tried a direct approach. Maybe space itself is made of discrete building blocks. that leads to a theory with a very literal claim. Look, quantum gravity. Geometry has atoms. Now, look, quantum gravity is one of the big attempts to quantize the space-time. The idea is bold but simple. Don't quantize matter first, quantize geometry. In this theory, area and volume comes in its smallest possible units. Space is not continuous. It's like a woven fabric made of tiny loops. The fundamental structure is called a spin network. Imagine a network of nodes and links. Nodes represent little chunks of volume, links represent chunks of area. Here's the twist that makes it feels like space from bits. These networks are not drawn inside a space, they are what space is. No background grid, just relations. So even here we see the theme. Reality might be built from more from relationships than from stuff. But the biggest shove toward information did not come from the loop theory, it came from the black holes, because black holes forced physicists to treat information like something physical. Now, black holes sound like astronomy, but the real drama is information. In the 1970s, physicists realized black holes have temperature, and that means they have entropy. Entropy is the measure of how many microscopic configurations correspond to the same macroscopic object. In plain language, entropy counts hidden information. Jacob Bekenstein made a discovery that felt wrong at first. A black hole's entropy is proportional to the area of its event horizon, not its volume. Let that land. If you think like a normal human, you'd assume more volume equals to more storage. But black holes say no, the information capacity scales with surface area. This suggested something insane. Maybe everything inside a region of space can be described by information on its boundary. This became the holographic principle, and once physicists accepted that, the question changed. It was no longer just what is space made of, it became, is space itself a kind of information encoding? Now we reach the modern core, because there is a framework where space from information is not just a vibe, it's mathematically precise. In the late 1990s, Juan Maldacena proposed something called ADS-CFT. Don't worry about the later, here's the idea in human language. A theory with gravity in volume of space can be equivalent to a theory without gravity on the boundary of that space. Two different descriptions, same physics, like two languages describing the same movie. In this duality, geometry, distance, curvature, even black holes, is encoded in the quantum information of the boundary theory. And crucially, entanglement plays a starring role. Entanglement is when quantum systems share a linked state. Not just they correlate, their descriptions become inseparable. Many physicists now suspect that entanglement is the glue that creates the feeling of space. More entanglement, smoother the geometry. Less entanglement, geometry breaks. So we are arriving at the big claim. Space-time may emerge from patterns of quantum entanglement. And entanglement at its heart, quantum information. That is why people say it from bit, or updated from for the quantum age, it from qubit. Now we can finally answer honestly, do we know space-time is made of quantum bits? Not in the way we know the earth orbits the sun, but here's what do we know. Smooth space-time plus quantum mechanics leads to infinites and paradoxes. The Planck scale suggests a limit to divisibility. Black hole tells us information is physical and tied to an area. Holography and ADS-CFT show that geometry can be encoded in quantum information. Multiple approaches to quantum gravity converge on the idea that space-time is emergent, not fundamental. So the quantum bits idea is not random, it's physics being pushed into corner. Now here's the most important part for you. If this is true, the implications are massive. If space-time is made of quantum bits, then reality is not fundamentally made of matter. Matter becomes a stable pattern in deeper information structure. Geometry, distance, location, shape becomes emergent, and law of physics start looking like constraints on how information can transfer. Not mysticism, not spirituality, just an evolution of what physics consider fundamental. And then we reach the final portion that keeps theorists awake. If space and time are emergent, what is the underlying information structure that produces them? Is it a network, a code, a quantum computation, a web of entanglement? And here is the cliffhanger that makes this a perfect ending. If we figure that out, we don't just learn what space is made of, we learn what reality is made of. And that means the next time you look up at the night In the sky, you might not be looking at into an empty space. You might be looking at the visible surface of a deeper informational universe. If you like this video, hit like, share and subscribe. Thank you for watching this. See you in the next one.